In this video, we're going to look at these two examples, and both of them are going to give us limits at infinity in an indeterminate form. And we're going to look at two different strategies for how we can calculate those limits. So let's start with the first one, looking for horizontal asymptotes of this function. And if you're trying to find horizontal asymptotes, that means we're going to look at the limit as x goes to positive infinity as well as negative infinity. So notice if we were just going to kind of try a direct substitution method and see what's happening as x is getting bigger and bigger, you notice if we're looking as x goes to positive infinity, we're going to get, this whole term is going to get really big. So I'm going to say that's going to quote infinity. And then this term is also going to get really big. So I have quote infinity minus infinity, which is an indeterminate form, which means the limit may or may not exist. We're going to need another strategy to figure out what it is. And we're going to look at that strategy in just a second. It's going to involve multiplying by the conjugate since we have a square root. But before we do that, let's also just look at what happens at our limit as x goes to negative infinity. So notice in that case, because I'm taking the square root of 4x squared, that'll be kind of my dominant term in there. So I'm still going to be getting a positive value underneath the square root as x goes to negative infinity. And then I'm going to get minus a negative infinity. So I'll basically get a plus infinity on that side. So notice the limit as x goes to negative infinity, we can just say right away we know that's actually going to be infinity. And again, this notation is shorthand. The limit really doesn't exist. Infinity is not a number, but this notation is shorthand for telling us that as x gets more and more negative, that my function is blowing up to infinity. So really the only place that we might have a horizontal asymptote, since we don't have one as x is going to negative infinity, we might have one as x is going to positive infinity. So we're going to check that now. So let me clear some space. Okay, so now the trick here is going to be to multiply by the conjugate since we have a square root in one of our terms. So put this on pause and see if you can multiply by the conjugate. Alright, so if you remember, we've done this before with limits. My conjugate, I'm going to take this term and this term, those remain the same, and the thing that's going to become different is the sign. So instead of subtracting them, I'm now going to add. And if I do this in the numerator, I also have to do this in the denominator. And so now I'm going to get this when I actually do that multiplication out. And that was the whole point, or the whole goal in trying to multiply by the conjugate, is now I've gotten rid of, I've been able to rewrite this now as a fraction in some senses, and I'm now going to be able to look at this using some techniques we've already learned for evaluating limits. Okay, so now notice, if you were to try direct substitution with this, again, we're still getting an indeterminate form. I'm still getting, quote, infinity over infinity. But we have a strategy that we've learned of how we can handle this. So again, put this on pause based on what we've done in class. See if you can find this limit now. Okay, so now we have this form, and we know our strategy from class when you have infinity over infinity is we can divide through both the numerator and the denominator by the largest power of x in our denominator. But we have to be a little bit careful here because we have the square root in our denominator. So before we go through and try to divide anything out, what we want to do is factor out our largest power of x from the square root. So my largest power of x in the square root is x squared. So I'm going to rewrite this. And then notice I will still have a 4, and if I factor out an x squared from the 17x, I will now have 17 over x, and then I still have plus 2x. And so then this is going to become, okay, now recall that when I take the square root of x squared, let me put this here, this is going to give me the absolute value of x. So that's going to be x when x is greater than or equal to 0, and the opposite of x when x is less than 0. And that's going to be important here because that means I'm now left with the absolute value of x times the square root of this quantity, and then I still have plus 2x. Now, because I know I'm taking the limit as x is going to positive infinity, I know that I'm looking at this part of the piecewise function. So in that case, I know that the absolute value is just going to be equal to x, so I can replace that here with this. And now if you notice, we can actually just factor out an x from the denominator, and that will cancel the x in the numerator, because I have an x in both terms here, and then I have an x in the numerator. So I can actually just simplify this to become this. So at this point, I'm ready to take the limit, and you notice as x goes to infinity that my term here that I've highlighted, that's going to go to 0. And then everything else, I'm just going to get, running out of space here, but I have 17 over the square root of 4 plus 2, so that's going to give me a total of 17/4. So that tells me that I have a horizontal asymptote when y is equal to 17/4. Okay, now let's look at the second example. Okay, so now if I have a limit of this form, notice we can rewrite this like this, and notice this is still of the indeterminate form infinity minus infinity, so we need a strategy that will help us determine if this limit exists. And in this case, the easiest strategy, and this is probably the first thing that I would try, is you can actually factor this, and there's more than one way to factor it, so I'll show you one way, and we'll just talk through the other. This is going to be the same as the limit as x goes to infinity, and I can factor out an x to the 1/3, and then I'm left with 5 minus. So it's of this form, and now notice that we can take the limit of this as x goes to infinity as well as this, and so since x to the 1/3 is going to go to positive infinity, and 5 minus x to the 1/6 is going to go to negative infinity, their product together is going to go to negative infinity. So you can conclude that the overall limit's negative infinity, and if you noticed, we could have factored out an x to the 1/2 first if you wanted. We would have still gotten the same answer.